Here is a device, PN junction, which is for the simplicity I am taking P plus N junction, and therefore the P's of PO, that is Ns, are larger than Ds, and as I apply forward bias, which is equal to Vf, one of the assumptions I am making that all this voltage comes across the junction. Essentially I mean there is no voltage drop across N and P region, which are called neutral regions. There are no space charge, therefore it is a neutral. In those cases there is no voltage drop. This statement is not valid in reality, because we will see later if I draw the currents, the so-called diffusion current due to the gradients will terminate or will become extremely low by one diffusion length. Okay. Which means if that current is so small and the net current is very high, obviously there must be another current which must be taking care of the total current variable. So there cannot be a drop across N and P. There will be, but as of now I assume that the charge is not enough there, and therefore the space charge neutrality is holding, and therefore electric field in those regions are though small, taken as 0. In reality that exists. So this is typical carrier profile which I can get. Let us say Pn XNO is the carrier concentration which one gets after forward bias. Lot of holes will come from P region towards N region, and as soon as they enter this, they are in minority. Though it's not clearly shown, that's why I was trying to say figure is not showing as if they are in minority, and if they are in minority, they will start actually reducing themselves towards their equilibrium concentration, because this is a steady state situation. However, it is non-equilibrium has been created. System will try to return to equilibrium. So it will reach from its Pn XNO value towards its Pn XN, or which is PNO value, and somewhere here, say let us say this distance, 66% of this will be called the diffusion length, up to which the effect of diffusion will be stronger, and finally carriers will decay down due to recombination back to its equilibrium value. The equations we can write for this. Similarly, there are excess electrons on the P side, and since P's are larger, the N's will be smaller. So what does that essentially mean? That the contribution of electron current, if it is a P plus N junction, will be smaller compared to the, why it is so? Because the gradient there, the charge which it will get through will be smaller. They will say electron current in P region will be smaller than in hole current in P region. If it is very heavily doped, P plus plus, let us say, this N current will be even smaller compared to the hole current on the N side. So practically most of the current then we will say is due to the hole current. This is what I say, we will use this in emitter based junctions in PNP or NPN transistors. That we want to reduce this so-called current coming towards the P side, in this case, much smaller compared to what this will go into the N side. That can be achieved simply by increasing the one side of the doping much higher than the other. What is the other effect you will see in reverse bias? One of course is that current is smaller compared to P currents, but what else can show in reverse bias? That the capacitance is essentially due to the depletion, they are going into which region? N region, because it's a lightly doped region, depletion will sweep. Is that clear? So the capacitance is essentially due to the N side, so depletion width is almost equal to Xn sides. Nothing on the P, though it has to have so much something in P side. Why? Such it must hold good. Okay, QT must be equal to Qn. To do that, a very thin sheet of charge you can see charge density, but the width will be extremely small. So this effect of a PN junction to P plus N junction should be understood, that what will happen if the dopings are relatively different in the two. We will go into one more last part later. This I had shown here is essentially called homo junction. What does that mean? both sides of the X is equal to 0, you have silicon or germanium or gallium arsenide or same semiconductor. We can create a junction making two different semiconductors with two different gaps. If I connect two different semiconductors with two different band gaps, such junctions which you are called heterojunctions. There are very interesting devices made out of heterojunctions, and one of the major device which is used is what we call high electron mobility transistors. Typically what is the mobility of carriers? We say normal silicon 1350 or at best 1400 centimeters square per volt second. In case of heterostructures, one can what we call quantum confinements, and doing this we can raise this mobility to 40,000 to 50,000 centimeters square volt second. These are called high electron mobility transistors, HEMTs. So there is a game going on which materials junctions be made so that the electron mobility is very, very high. What's the advantage of higher electron mobility in circuits or devices? Speed of the device will be very, very high. So we are, of course, this statement will be heavily modified if I show you heterostructure. It's not that every time I can get 50,000. In certain cases, certain limited this I may, and such microprocessors have been made using HEMTs. They are very expensive and used only by NASA as of now. Because of their space program, they need extremely high this. There are many other problems it creates, but they are taken care as far as they are concerned, not everyone. Okay, so let's look at excess carriers. So we are pushing excess holes, we are pushing excess electrons, and they will follow continuity equation. Okay, they will follow continuity. What is the way we write? If delta Pn is the excess carriers, then this term is 0. Excess carriers actually with time dependence will be equal to 0, and if that's so we can, please remember delta Pn is equal to Pn whatever x or y you call it minus Pn. Excess carriers. These are excess. This being constant, it's 0 anyway, so instead of writing Pn by dt, we can as well write delta Pn by dt if you need. And same way, if I write this, I will get dp, d square delta Pn upon dx square minus delta Pn by tau. This continuity equation we have already derived, we are just substituting back here. If that's so, and if this is equal to 0, I can then find delta Pnx, and if I calculate delta Pnx, what I can then calculate? dPn by dx, and if I get dPn by dx, then what do I get? The diffusion current. So my ultimate aim is that whenever excess carriers are injected from P side into the N side, the holes will start diffusing in the N region and will constitute a current which we call diffusion current due to holes. By the same argument, the electrons which will come from N side will diffuse into the P side, and when they diffuse they create a gradient, and therefore they will create a diffusion current of electrons on the P side. The net current will be how much? The Jp diffusion plus Jn diffusion. Total, because they are opposite direction with the charge sign separate, so we say the total current is always sum of electron current plus the hole current. So we will derive one equation and say okay, similarly for electrons on the P side, and then this is the net diffusion current. So what is the solution of such equation? It can, okay, you can write dP here, make it this, and then dP tau p I can replace it by Lp square. Okay. Is that, I have a duster, so I could say that. You may write 2 steps. dP will be first put low, and then dP tau p is Lp square. Okay. So if I solve this equation, which is shown here, it gives me a relationship x minus ln. Sorry. Now, to get this A and B constants, we must get two boundary conditions. Okay, we need two boundary conditions. But the first boundary condition, which I said, x tends to infinity, or xn you can call it if you wish, if it is inside I am talking, then this term will go to 0. Okay. But to this term, this will go to infinite. So what is it that means? That e to the power x by Lp going to infinite means the excess carriers will actually start rising. But what did we say in diffusion and recombination? The carriers will decay down to get to equilibrium. So obviously for this condition, equivocally, A must be 0. If A is not 0, then e to the power x by Lp term will actually enhance the carrier concentration. The other one will go to 0 and this will enhance. And in no way diffusion can enhance the carriers. And therefore, we say A is equivocally 0. And then to get the second boundary conditions, which I wrote yesterday, let me just copy quickly because we have too many things to do and I think I am going very slow comparatively. Okay, the other boundary conditions we wrote at xn equal to 0 or xno you call it. The boundary condition is p's of n at xn. Did you realize I have derived it yesterday? Pno e to the power q vf by 8. This is what yesterday we derived. Okay. From where we derived this? That the concentration ratio should be proportional to e to the power barrier potential. So V0 minus Vf in one case and V0 in the first case without and with bias. Ratio of the two will give me this relationship. If this is the relationship, then I substitute here and then I get the relation finally Pno e to the power qvf minus by kt minus 1 and this is now Pnx. Okay. Or rather even right now you can keep, let's see whether I am right, but maybe we'll just check that. E to the power xno minus x by Lp. At x is equal to xno, this is 1 and this is the excess carriers at xno. Okay, this condition. At x is equal to infinite, e to the power minus infinite is 0, excess carriers go to 0, so equilibrium value is 3. Is that clear? So this boundary conditions are met if I write the solution as delta Pnx is this. Please remember what is this value? This value is this at the edge of the transition region or depletion region, wherever they enter the neutral region. This fact, once I know this fact, what can I do now? Similarly, I can write delta npx or minus xp if you wish will be similar np0 with a sign correctly taken e to the power qvf by kt minus 1 e to the power x plus xp o by ln. What is the boundary condition the other side? xp is minus xpo, ends of p at minus xpo is npo e to the power qvf by k. This is one boundary condition, this is two boundary condition, this is third one, and xp minus xp tends to infinity. Two for this side, two for this side. So I can always calculate the excess carrier concentration on P side as well as on the N side. And once I know my excess carriers, the diffusion term can be easily evaluated because Jp is equal to how much? Minus q dp dpn by dx. So once I derive these two expressions, okay, this is called steady state. What does that mean? the bias is constant, bias is constant. But in real life, what will be the bias? Bias you may keep, but some signal will be coming to you. What is the kind of signal I can use? Either sinusoidal or square wave. In either case, the signal will be overriding this so-called DC value which I will apply. So what will happen? This condition, it will be time dependent solution, because it's a time dependent solution, because now it's varying. Okay. So then that dN by dt and dP by dt terms are really not zero, and then one has to solve more rigorously such equations. Okay. Right now in our case, it is a steady state. Once DC bias applied, the system as if remains universally time indifferent. This is our assumption, to some extent correct, and therefore we can use this, and once we derive this, the rest is very simple. Can I rub this part? This I want to keep, and this of course we have done already, 4 boundary conditions. So if I want to find the J, P and X, is minus Q dP d, since PNO is constant, dP by dx is d delta Pn by dx. And if we differentiate this last term and find the current at say XNO, I want to find the current entering here at that point. Then I do this analysis and I get this equation. You do yourself and verify. Q dP PNO by LP e to the power QVF by KT minus. This LP is coming differential of this 1 upon LP is going that side. Okay. Minus sign which is coming from here is that minus will cancel, so therefore plus Q dP PNO by LP e to the power QVF by KT. And let us say QVF by KT is very high, or VF is larger than 1, you can always neglect 1 as far as number goes. Otherwise keep this value. E to the power 40 minus 1, if you can put it to the some million minus 1, is okay, your choice. Otherwise numerically that may be neglected in many cases. As I say, KT by Q at room temperature is how much? Q by KT around 40, 39 point something. So 40 times 0.6 volt is 24. E to the power 24 is a large number. Is that clear? So one can always be neglected as far as forward bias is concerned, but keep writing till you find out it is smaller. Okay, so similar argument I can take. So I have figured out this current which is entering. So maybe if we extend this figure down, which is very important for us. Let us say this is my net. Okay, if I want to find currents, what should I do? Let's say A is the area. Just multiplied by area. Okay. What is the area in a device from there? This is 2-dimensional figure, for example, shown. This is the kind of device. This area is the area, cross-sectional. Is that clear? So assumption is that much uniformity is maintained along the third direction as well. So we just multiply it by area. Okay. So if that is not uniform geometry, please do not multiply area like this. You then have to probably integrate it out to get the net current. But for first order in evaluations, this is good enough. So what does that mean? That I got this current, let's say I is the total current. Okay. across the device. At this boundary, wherever I have, okay, maybe I put it something like this, the current, two boundaries I say, from here it goes down to how much? By this relationship. Please remember this is at xno, but at x, e to the power x by LP term will appear. It will start decaying the current as I increase the distance. The current, this is my IPX current. This is my IPX current. Is that clear, Papa? As the carriers decay, the current will correspondingly go down. E to the power x by LP equivalent terms. Okay. Now, the net current is I. So, there must be equivalent current from electrons which must be making this current, because I keep saying at every space point the electron current plus hole current must be equal to the total current. If the total current is constant and if this is the hole currents, the remainder current must appear from electrons. So, the electron current may sometimes look something like this. Same point. So, it should be complementary of that. As it decays, by same way it should increase, and this is my INX. Now, we have not talked about this current coming from where. You get the point, my worries are, and that you should think over it. होल्स तो डिफ्यूज हो गए, तो आपने डिफ्यूजन प्रोफाइल निकाल दिया, डिफरेंशिएट कर दिया, डिफ्यूजन करंट आ गया, उसका कॉम्पेंसेटरी करंट इलेक्ट्रॉन्स करंट कहाँ से आ रहा है, तो वो थोड़ा सोचिए, नहीं तो थोड़ी देर बाद बता. Is that clear? Because I have said my first assumption is I is constant throughout the device. Now you say whole current is decreasing. Obviously electron current must be rising to make it net current at the end of it. After this, the whole current is actually as if picked up by only electrons. Is that clear? Because the whole current has already subsided. Is that clear? So, if this current has to flow, what is the kind of current? There is no gradient there because this is constant. Okay. So drift current must be occurring there. Drift current must be occurring there to pull this electrons now towards the contact, such that there is a net current available. Is that clear? That means the electric field in N region is not zero. I started with saying neutral, no field, but if there is no field, there is no current. So this is something called, let a pinch of salt, you accept theories, because in reality the current is constant. You see it, you get bias, you don't have to see which current, I is constant, kaisa bhi karo. Internally, so it must get balanced. By similar argument, I can do it for electrons, if this is my electrons current, IN XP, then equivalent current must appear from here, which is my IP XP. Because what is our criteria we started? Net current is constant. Is that correct? Net current is constant. Now this is something interesting to think how this. So I always will come back to it a little later why these are occurring. But this fact has to be understood that I only have to find IPX or INX, INXP, and then subtract it from the total current to get the other currents. I minus IPX, I minus INXP. That will be giving you the other currents in the regions you have. Now this is very interesting as far as the theory goes. But you can see something I have done it by my concentration profiles. Do you see something happening here? थोड़ा कम दिखा है. I intentionally showed you there. That means even when the holes reach from their equilibrium value closer to the transition region, they create a gradient. Why? Because within one diffusion length they will recombine. They will recombine. And if they recombine, they will create a gradient, and that is your whole point. By similar argument, electrons, as they reach closer to the junction from the n side, they will recombine in its diffusion lengths and they will give you a small gradient, which itself is compensating the other current. Is that clear to you? Is that clear to you? So you must remember that why books show you this and then. This is because if that does not occur, this compensation cannot be explained. Is that? But beyond this, obviously there is no diffusion. Carriers are already this, so they must be drifted out. Okay, so the rest of the current must be the drift current due to the electrons, and we will see this little later. So is that issue clear to all of you? That in PN junction, this is interesting area that closer to the junction again recombination takes place, but not, what is the criteria we have so far said? There is no recombination in transition region or depletion region, because we say all of them which enters will be picked up here. All of them enter here will be picked up. However, in real life, even this statement may be not true. The transition region or depletion region may have certain amount of trap. Okay. Because silicon cannot be trap free. Which traps have very strong probability of recombination? Near EG, near EI, that is halfway they are both electron and hole have probability to be captured and recombined. Which are these traps called? Recombination centers. So if you have a recombination centers present, which will be there, some of them, then there will be a recombination term or maybe generation term even in depletion region, and we must find out that. So now you get it. If I use only this relationship, which kind of current I am looking for? So the total current, maybe you can write QA EP PNO YLP plus QA DN NPO YLN into e to the power QVF YKT minus 1, and this term is given a name saturation current IS, which is IS times e to the power QVF by KT minus 1. This is P current. I told you at any time total current, whole current is here, electron current is going at near the transition region. XPO plus XNO current should be total current. At XPO and XNO the current should be sum total. This is at one end, this is at the other end. So total current is sum of these two currents. This we have derived, so we know these currents. So we just add them to get total current. This value is called saturation current IS. Now just look at the situation in reverse bias. We have forward bias the device. Is that clear, Pawan? We have forward bias the device and we still assume VF is not very small. A little bit sufficient amount of carriers are injected. Can you see this value IS? If I say VF, which is forward bias, and I call VR as reverse bias, which has a negative sign. So if I change the polarity here, let's say I put plus here and minus here, what is the device will be called? Reverse bias. So the diode gets reverse bias. If I substitute this value here, I is equal to IS e to the power QVR by KT minus 1. So even if VR is the order of few volts or less than, more than 0.1, 0.2 volts, e to the power minus QR by KT will be much smaller than minus 1. So practically this will give me Is that correct? So under reverse bias, I do see, now the question arises, can I justify now, this is where the issue was. I said I have used this equation assuming that in reverse bias, this does not change. Is that correct? This does not change. But if this changes, then this whole statement will go awry. Is that correct? So now I must prove that though it may not look similarly as I shown here, under reverse bias, the concentration profile should be such that it may lead to a current which is QADP PNO upon LP plus QADN LP upon this. Same value I must get. If I get that value, then I can say the forward and reverse characteristics of a diode will, at least initially I don't know, but from here onwards, this region, maybe this region, will show you proportionality QVF by KT, and on the reverse side, I will get a constant current of IS. Please remember, IS is independent of bias. IS is independent of bias, the way we have done it. Okay. Except where? Except at this point, it is a function of VR because e to the power minus QR will be some value. So it will actually start rising as, but once VR becomes larger, this term will be very, very small. So practically, what I see in the reverse bias, the current remains constant, which is the reverse saturation current. So this S word was given from this reverse bias current, which is called reverse saturation current, which is constant independent of voltage I apply. But I yesterday showed you, or told you, or maybe earlier, that it is actually not so. The current is increasing very slightly. Okay. That means there is a voltage dependent term additional to this constant current. Okay. Two currents. Is that point clear? One is independent. But if I see some variation, that means there must be additional mechanism which is voltage dependent, which is making the reverse saturation current as voltage dependent term. Similar argument I figure it out. If I see this small region of voltage or lower region of voltage in particular, I find this has relationship of this. I see that the initial relationship is slowly rising, which means e to the power QF by 2 KT is slow rise, KT is faster rise. So initially slow rise, then rises. And I told you earlier that if I increase further currents, which is called high injection, I again see e to the power QF by 2 KT terms. So initially small, faster than again, and finally, as I say, it stops almost rising, which is called ohmic regions. Now this, why this slopes change? In most cases of the circuit, you will never reach this value, or you will attempt, there is something in circuit, how do you limit the current? Oh, I already said the word. How do you limit a current in a circuit? What is current is essentially V by R. Okay. You have a circuit resistance or something R, plus you add your resistance, that R plus R dash. Now this, even if R goes to 0, V by R dash will have a limited current for you. Okay. This is called limiter. Okay. This is called limiter. So all circuits should have a limiter, because if battery shorts or your some component shorts, it should not burn any time. So alternately, you should have a fuse everywhere which blows when the current starts rising. So this limiter will never allow currents to go to high injection levels. But theory wise, if they do go, there is a possibility of slope changing ahead. That will see, that doesn't make, that's very easy to understand. But the problem which I see here, the phenomena which I am going to work here and work for this slope seems to be identical. That is the fun part. So two things I have to prove. One is this Is is same as this value which I got, and second, this e to the power QE by 2 kT is also shown here. So the phenomena on the forward and reverse must be similar if not same, or maybe same. We will see whether they are same. What could be those phenomena? Could be same if I say, in one case, something in reverse it is going in case. One is the term which we call recombination terms, the other is due to the increase of current, na? Please look at it. This is increasing current from this. So there must be recombination terms happening there. This is enhancing the currents, so must be, generation must be occurring. Generation and recombination are same, G is minus R or R is minus G, from the same place if it is occurring. So we say if there is a recombination this side, in reverse bias it must be generating, and therefore it must show you QE by 2 kT. Is that clear to you? This is what we have to prove, and if we do so, I think we have achieved what thing first. Okay, so first, can I rub this? Let's see bias. If I apply reverse bias, what will happen to the barrier? How much will be barrier? Band diagram wise. If VR is the reverse bias, so if I show you a band diagram, and this must be QV0 plus VR, because now polarity of the external polarity and this polarity is actually similar, and therefore electric fields add, therefore voltage also adds. So net potential barrier now is this in equilibrium. Okay, this is my, let's say, EFN. First let me draw the figure and then we'll see where this should occur. Okay, if the Fermi level of P type, please remember where the Fermi level of P type and Fermi level of N type. If I actually increase the barrier, that is I apply negative potential to P and positive potential to N, electron energy in N will decrease or increase? जरा देखो ना, पॉजिटिव पोटेंशियल था तो इलेक्ट्रॉन एनर्जी क्या हुई? कम हुई. अब क्या हो गई? ज्यादा हो गई. That means the electron energy is higher on this side. The Fermi levels, there should be which way split? Please tell me which way the Fermi levels will be. EFN will be where compared to EF, or with reference to EI, where should be EFP and where should be EFN? ये इसके पास होगा या उसके दूर होगा? EFN दूर होगा तो उसके proportionately EFF जो है वो ऊपर आ जाएगा. Is that clear to you? So that means the change in this voltage, change in this EFN to EFP is UVR. पहले इसमें कैसा था? इलेक्ट्रॉन्स ऊपर गए, होल्स नीचे आए. अब उल्टा किया, बैरियर उल्टा किया तो Fermi level in P type must be higher than N type so that the barrier energy is now enhanced. This means now an electron or hole to electron to come here or hole to come here will be even more difficult. Diffuse करने के लिए पहले ही V0 ही रोक दिया था. Now we have or further enhanced it or hill बना दिया. So holes are, my goodness, kind of. So obviously we say practically very little or zero diffusion current needs. Is that correct? Even V0 it was stopping. If you increase this V0 to V0 plus VR, it is unlikely that electron will acquire much energy to climb and go to the p side, or holes come from p side will go to the n side. So what does that mean? If there is a very little or no electrons hole can go by diffusion, which current will become zero? Diffusion current, because there is unlikely that pure electron holes can then, of course there is a marginal diffusion current, will still move. Probability wise some carriers can always go, so they will go, but that is very small. But the current is seen. So which currents can be seen now? Now we can see from here what is happening in real life. Okay. If you say now, this is still PNN, there is no carrier coming from P side to the N side. So what is the whole concentration at XNO? इधर से कोई carrier आ ही नहीं पा रहा है. So let's say this is my zero value. Okay, this is XNO and this is my zero on this side. So here the excess holes are. Is that clear? Zero. Holes cannot come here. So at the boundary there are no holes available at this point. So this is zero. However, away from the space charge, what is the carrier concentration in the rest of the N side? Equilibrium. So obviously, whatever is the PNO must be of this kind. Must be of this kind. Similarly, there are no electrons coming here. At the boundary, no electrons are coming from N side, so the electron concentration is 0, but equilibrium is NPO. So now what is the kind of profile you see compared to the first one? Opposite this, but they still create the gradient. Is that point clear? They still created the gradient, and once there is a gradient, there will be carriers to flow. Is that correct? So don't think there is no current. Current will come simply because this. Now, one technique which I have not done in the forward bias, can you think in the case of forward bias, this was a PN, whatever we call it, PN XNO, so this PNO, what is the charge stored here? Q, A, let's say this is my XNO to some value Ln, Lp, up to which this exists, or take it to infinity if it is reaching infinite. So you say XNO to infinite delta PNX dx. Is that correct? This is the charge stored in this region, and if you integrate by substituting this, you will get EP on LP. Sorry, how much it will be? No, integrate charge in this. Net carrier concentration multiplied by integrated over that region is the charge now injected into the N region from P side. Total charge injected. Okay. Please remember what he is saying. I think I did not make it clear. I have injected holes from P side into N side. They are decaying because of recombination and diffusion terms. But steady state, the profile remains constant. So how much is the injected charge? Area under the curve. Area under the curve. So integrate out. Okay. Integrate it out. And this integrated charge, if I know, then what is the current? Or Q by tau. Tau is the recombination. So as soon as I evaluate Q by tau, I must get the same current which I was getting earlier, because this phenomena was also taken care from the diffusion term itself. So one method of evaluating currents, is that point clear, madam? Why I am interested in Q? Because you have done an experiment recently, I am told, that diodes on off switches, and you say there is something called storage time. And time is storage because of what stores? Stores can be only charges. Okay, so there is a charge storage going on, and in reverse bias what happens? This stored charge has to be removed before, and only then diode can become reverse bias. So the time taken for this forward bias device, which is now externally reverse bias, this charge must collapse because your device still remains forward bias internally, because there are positive charges, negative charges sitting there. The time of collapse of this charge is called the storage time. Is that correct? That's what the word is, storage, because that is the time before which this cannot collapse. And once that time reach, recombination will take care to get it to saturation. This fact that charge storage is important in all switching devices. Is that correct? There we are only interested in how much charge, how fast I take away. Okay, that is exact, or how much charge I can pump fast. Because larger the charge means conductivity is higher, so smaller drops. So I am looking for in any device how fast I can inject and how fast I can retrieve. Okay. This fact which I am saying is not very easy to attain, because it will, in one case will require smaller lifetimes, the other case will require larger lifetimes. You cannot have a device with same time both lifetimes. And that is where switching devices are not good gain devices, and not good gain devices are not good switching devices. You need one for the other. Okay. So this fact has to be, so that charge theory, which I forgot to tell you, is equally relevant in our calculations, because Q by tau is current. So we evaluate the charge stored there, divided by lifetime there, and then find out if I do find out, okay, maybe I have the value if I have, I don't know whether I have solved this problem quite some time back, which I did. Okay, the value which I got is, I have value. QP is QA, PNO, LP. This is volume, this is concentration, Q into charge. So this is QP. Please take it. Is that correct? This A into LP is the volume, per unit volume, so cancels. Charge into numbers, okay, is the charge density there, net charge there. And if you divide it by A, then what will it happen? Then this will be called charge density, as the word goes, Q. So it should be called QP dash, because then it is actual charge in coulombs. Now this charge, Q dash, P by tau is equal to I. If I multiply here divided by tau P, and to do this what should I do? I multiply dP here, I multiply dP here. What is dP tau P? LP square. This LP and this LP can be removed. थोड़ा मैथ्स करके देखो, ऐसा कोई बहुत बड़ी बात नहीं. That is the value which I got, QADN, and this is a minus sign because Q is a minus this. So finally, you will get IP is QA, of course e to the power that will exist, QA, DP, LP, PNO, e to the power Q, यहाँ भी है, e to the power इसमें भी है, df by kt minus 1, same current आएगा. So if you do this analysis, you do the same method. So I apply that method here. Okay. What do? I apply this method. I integrate from XNO to Ln only or LP only. Okay. Similarly on this side. If I integrate this charge and divide by tau, this current Is is actually I am getting QA, of course it's a minus sign total, QA dP PNO upon LP plus QA DN. ये करके देखो. If I do the same analysis with the same excess carrier profiles as I did there, repeat for a reverse bias, evaluate charges there, divide by tau, find out the net current there, and you will be surprised. And then why V doesn't come there, e to the power minus VR is much smaller than 1, so minus sign taken care. So you will get this current which is saturation current in reverse bias. Derived from which equations now? For this case, is that correct? For this case, but it happens to come same as what I got in the case of forward bias. So now I can satisfy myself that I is equal to Is e to the power qv by kt minus 1 is universal. Is that clear? Is that point clear? In reverse bias I get same Is, in forward also I get same Is. So I say okay, then I can always write I is equal to Is e to the power qv by kt minus 1 is universal for left reverse bias as well as for forward bias. Still one assumption we have not done. What is that assumption we have not done in this case? In the space charge region, there is no recombination or generation occurring. Whatever is injected is received, whatever is injected is received, and therefore, now this part which is very interesting. What we are trying to say now, that okay, you have got this current fine, but why the carriers are still moving in the reverse bias? There must be electric field which must be drawing them. Please remember how this, you have electrons here and holes here, they must be taken away at the ends. So in reverse bias, there will be an electric field which will pull these carriers to the ends and will constitute reverse saturation current. Is that correct? So this fact that electric fields are zero should be always taken with pinch of salt, because otherwise the carriers cannot be brought to the contact. Is that point clear? This fact is very crucial in all designs, that there is an electric field in the neutral region which is very small but necessary for carriers to bring to the contact. But as far as its value is concerned, we can still treat it very small, equal to tending to 0, and then solve the all together. Is that clear? These two facts are not correct, but should be mentally adjust करो कि ऐसा ही है, ऐसा होता नहीं. Okay, so time is up.